Hello and welcome to this Aerospace Testing International and VTI Instruments AMETEK webinar. My name is Ben Sampson. I'm the editor of Aerospace Testing International magazine. So today's webinar is titled Signal Quality Matters when Designing an Automated Test System. This webinar will explore the role of automated test systems when testing and verifying line replaceable units, otherwise known as LRUs. We're lucky to have with us today to give the webinar Nathan Henderson, who is Senior Applications Engineer with VTI Instruments and AMETEK Programmable Power Brand. Hello, Nathan.
Hello, Ben. Thank you for the intro. So yeah, today...
That's quite right.
Sorry?
Please go ahead, sorry.
That's okay.
Go ahead.
Yeah, so today we want to be talking about ATE or ATS, automated test systems. And I'm sure a lot of the people in the audience here will be very familiar with these and their important role in the aerospace industry.
Sorry, Nathan, I should have just reminded the audience there that if they have any questions, to write them in the box on the right-hand side of the screen during your talk, and we'll get to them at the end. Thanks.
Okay, that's fine. So let me just jump into what we've got here as our agenda. One moment, if I can get my presentation to work. Here we go. Right. So what I want to cover today, a basic introduction to automated LRU testing, and also part of that LRU testing, what is switching and why do we need it? And then the importance of signal quality within our ATS, automated test system, how to achieve good signal quality. And I'm going to break that down a little bit because that's quite a vague subject or title like that. So we'll look at wire routing and connector selection. We'll also look at relay selection, PCB design, and then a few other parts that really affect signal quality, such as bandwidth, insertion loss, and also transmission of signals through single-ended or differential methods. And then right at the end, not directly related to signal quality per se, but we'll look at some industry standards that you can apply to building an ATS or ATE system. So the first part, and I'm sure everybody on the call will know that an LRU or line replaceable unit is the name given to aircraft avionic components that are replaceable first or second line during service, or if there is a fault reported. They are generally black boxes that cover anything from radio to radar, engine controls, navigation systems, anything like this. And they tend to be an easily removable item that you can get in and out of the aircraft without requiring any extensive disassembly. And then the purpose of the automated testing of these is just to streamline that testing process and to ensure that all these boxes are in their correct working condition after installation or before maintenance, or if a fault is reported or something like that, then we can quickly test them. Before the days of these being an automated test, it was a long process to manually take the test equipment to the aircraft or the aircraft into the hangar, and then manually plug your way through each test point and test the system. The trouble with manually testing is there's a massive risk of connecting to the wrong pin or giving it the wrong signal and ending up with errors in your test results. The idea with automating our test is, one, we reduce these errors, but also by automating it, it's a massive reduction on time needed to do so. And by automation, we also add repeatability to our testing. So I'm going to quickly cover what I've put down as the 4 sections for an automated test system. It's not a complete list, but it's certainly the 4 larger parts of an ATS. So the first part I want to look at, interface and connectivity. This is not only the physical connection to the LRU, bearing in mind that an LRU will have upwards of a 200+ pin connection or connectors to interface with the rest of the aircraft. So it's the physical connection to whatever connections that it has. It also covers the communications or protocols needed to communicate with that LRU. And beyond that, they're not necessarily wired connections. Sometimes we see wireless connection as well, depending on what the LRU is doing. And so the ATS has to be able to establish these communications and connections. The next part is software, and each ATS is going to be bespoke for the LRU that it's testing, and the software very much follows that as well. And so your software will include a database of tests, and those tests and test procedures will follow the manufacturer's requirements to test those instruments. The software has a second part to this as well, where it will data log what it stored from your test. And then beyond that, it will create reports, flag up errors, and run any calibration adjustment or anything else like that required as well. Third part, data acquisition and signal generation. And for this, we generally see the front of an ATS being a large 19-inch rack or something along those lines. And for data acquisition and signal generation, we tend to think oscilloscopes, digitizers, function generators, DMMs, and DIO, etc. The list goes on. And the form factor, whilst we're talking 19-inch rack, it can still be benchtop type equipment, but with rack mount ears and things like that added to it. There's also a large portion of modular systems, and we tend to see VXI and PXI as the most common modular systems that you'll get on these. There are beyond that proprietary modular systems as well, which are designed for specific tasks, and we'll look into those a little bit further as we work our way through this. We tend to invest a lot of time and expense on the actual data acquisition signal generation side of an ATE, and there's a big reason for that, really. And it goes along the lines of, if you were calibrating or testing a 6.5-digit DMM, you'd need an 8.5-digit device DMM to complete that test at minimum. So what it means is your ATS or your ATE needs to be more accurate than the LRU that you're testing. And so high specification digitizers, function generators, and that side of equipment are often put into these. And then finally comes switching and signal routing. And by signal routing, I'm also referring to connectors and cables and everything that interfaces between your LRU and your actual test equipment, communication buses, and everything else you've got in there. So in order to link multiple inputs and multiple outputs together between your LRU and your test system, you need some sort of specific switching system or something in there to link everything together. And the purpose of this switching really is just to enable maximum use of your equipment to the device that you're testing, with minimal or if zero reconfiguration needed between each test. And an example of why you'd really need this switching, let's say on our 200-pin connector on the back of our LRU, we want to make 50 voltage measurements. Now, the manual way would be you'd sit there with a DMM and connect to each pin and take your 50 measurements. Another way could be that you'd end up having to get 50 DMMs and connect each one directly to the 50 pins on that LRU to do that. Or alternatively, we can use switching to sequentially scan one DMM past the 50 test points. And that's what we're going to cover further as we work our way through this presentation. And switching relays are the preferred method to achieve this. So when I'm saying switching, I'm not talking a physical switch, as in a toggle switch or a push button switch or something like that. I am talking an actual relay. And when we look at relays, there are three general types. We have mechanical relays, read relays, and solid state relays or switches. Mechanical relays use a copper coil as an electromagnet, and this pushes the has a plunger that pushes the contacts to make and break. It's a bit like a solenoid. Physically, it just generates an electromagnetic field. It pushes or pulls a plunger to open and close contacts. Generally, you have a spring-loaded or spring acting on those contacts. So when you remove the power, the contacts go back to their default position, whichever that happens to be. They come in many sizes, from enormous ones that can handle a few hundred amps down to sub-miniature surface mount devices. So it covers a big range. read relays are still a electromagnetic device, but they operate in a slightly different way. So a read relay, I've got an image here on the right as well. Basically, it has a copper coil wrapped around a glass tube, which is known as the reed. Within the reed are two steel wires. When you apply power to that coil, the two wires inside are either attracted or repelled, and they therefore make or break the contact. And then the final type of relay selection that we've got here is the FET or transistor switch. It's a solid state device, and quite often we use an opto-isolated version. Therefore, there's no risk of getting whatever your signal is that you're trying to switch back into your control circuit. And that pretty much covers what we have in the way of options for switching. Now, yeah, it's 2023, and everybody will say, well, why don't you just use a solid state switch? Does a mechanical relay or a read relay really have a place now? And the answer is very much so, yes. Yes, they do. And there's a few reasons for this. So, I mean, first off, we understand solid state has an exceptionally long, if not infinite, life of connecting your signal. There's no moving parts inside. Also, it's by far the quickest way to turn on and off a signal. However, there are other issues that come with this. And it falls down to what sort of measurements you want to make. For example, if you are looking for measuring a low voltage or a resistive measurement or something like that, then a solid state relay is almost unusable. And the reason for this is that it suffers very high resistance when you switch your signal with it. So when you put it in the path of your signal and you turn it on, it will increase or add a resistance to your signal path. Secondly, they also suffer from leakage. That is, the power used to switch them will find its way into your signal path as well. So if you've got an increased resistance, or you don't necessarily know what that resistance is from switch cycle to switch cycle, and you've got a current leakage into your signal path, then it's not really conducive to making good measurements, certainly for lower resistances or lower size signals, shall we say, small voltages and things like that. And therefore, even today, when you're looking for maximum signal quality, minimum resistance, then you're looking at the mechanical type relays to achieve this. The downside is that they do come with a reduced life, and they're also a little bit slower to switch your signal. But when it comes to actual signal quality, mechanical really is the way to go. So as a quick recap on just the ATS as it goes, we understand that they have a large number of test points that need to be connected to your device under test, the LRU. So we have a range of oscilloscopes, DMMs, and function generators, etc. And we have a range of inputs or outputs on the LRU that need to be connected sequentially to run this test. If we have switching, then that enables us a large amount of flexibility to test different parts of the device under test without having to physically reconfigure the setup. We don't want to start to head towards that manual testing again. We want to connect the LRU, we want to press go on the software, and we want to report at the end without having to do anything in between. So if we look at switching, and due to being a very custom part of your ATS or your ATE, generally switching comes modular. That is, you get actual switch cards. So it's a PCB with a collection of relays on board. It then becomes a fact that you need to be selecting the correct type of switch for the task that your ATS is doing. And we'll cover that a little bit further as we work our way along, but just getting any old switch card isn't necessarily going to work for you. So let's just jump to that and chat about the different types of switch card that we have here. So being a card, there are three basic configurations. They're all using the same relays, but the relays are configured differently as to how they interface with the front panel connector. So you get your basic switch card, okay, and I've got the image in the top right here. That simply is one input, through a relay to an output, the most basic form of switching. And generally, the basic switch is used for more high power applications. So if you're switching the power on and off to your LRU, that's the type of switch card to go for. The next type is the multiplexer, which I've got as the next image along here. The multiplexer allows you to link multiple inputs to a single output, or a single function generator to multiple inputs, whichever way around you want to run it. But if we took it back to looking at, let's say, that DMM and making 50 measurements, this is the card that you would really work the best for you, because you can connect your DMM to the two analog bus lines and then sequentially close and open each relay connected to each of your voltage pins on your LRU and take a measurement. This way you quickly scan the DMM across your 50 points and you take your measurements. And then the last type of configuration that we'll cover here is the matrix. Now, a matrix has the ability to connect any input to any output in any configuration. So it offers by far the largest amount of flexibility. So it could be said that, why do you need to use a basic switch or a multiplexer when a matrix already exists? Because the matrix can do what the other two do, and you just need the one card, which is true to a point. The thing with the multiplexer to understand is usually they cover a few hundred channels, therefore the relay size isn't huge. And because of that, they can't necessarily handle the same amount of power as you could with a basic switch. And the second part to the matrix is you need to be careful how you're signal routing through a matrix, because you want to use as minimal amount of relays in your signal path as you can. The multiplexer works very well for this, because your signal only ever goes through one, maybe two relays maximum to get to your end and connection point. With the matrix, you can be putting multiple relays in your signal path, and we'll cover why that isn't necessarily a good plan, and also therefore why making sure that you have good signal routing through your matrix becomes important. So let's have a little look at why signal quality is so important on an ATS, and then we can carry on and understand how we achieve that. And like before, when I said you need, as an example, an 8.5-digit DMM to be able to test a 6.5-digit DMM, your ATS needs to be of a higher signal quality than the device you're testing, or a higher resolution than the device you're testing. And the primary goal of automated test systems is to accurately measure and analyze electrical characteristics of your LRU. If your ATS is creating distortion to the signals, or in any way, and by distortion I'm talking noise, crosstalk, insertion loss, impedance mismatches, reflections, and things like this, anything that you create in there is harming your measurement. Your software that is therefore running your ATS is therefore going to record results that are not correct. You end up with corrupt data. It may also lead to other issues. It could give you a false alarm saying your device isn't working correctly because it's not seeing the signal it should be. Or more concerningly, it could miss a fault that actually exists. And therefore, routing and getting the signal from your LRU to your source instrument, or from your source instrument to your LRU, becomes really important. And at that point, we need to really give the same amount of attention that we gave to our source or measurement instrument. We need to apply the same amount of signal quality requirements to our cabling, our connectors, and our switching within that ATS. Ultimately, it comes down to reducing noise within your system. The lower the noise you introduce, the greater your signal to noise ratio, and therefore the smaller signal variations coming from your LRU or going to your LRU, we are able to measure. So there's a few parts to this that I'll cover, and again, it's not an exhaustive list, but we'll look at a few of the big ones. the first one I want to talk about is bandwidth for your signal, or in the particular case of what I'm looking at here, baseband bandwidth. So baseband bandwidth generally means that you are looking at a signal from DC up to the megahertz or gigahertz range. Okay, and what we define as bandwidth for a switch card or a connector or a cable is what is put as the 3 dB point, or the maximum frequency that you can put through that cable before you get significant insertion loss or distortion. And the graph to the right kind of explains this. As you increase in frequency, so your signal after a set point starts to suffer insertion loss. As you can see from that graph as well, that 3 dB limit isn't a hard stop. Your switch card continues to work beyond this, but you will be functioning at a reduced power, maybe with extra noise or distortion. And also you can see that you're starting to lose signal power before you get to that 3 dB point. So if you're getting close to your bandwidth limit for your signal route, be it switch card, connectors or cabling, you're already starting to have a insertion loss or a distortion issue. And for the graph that we've got there, you can see that bandwidth and insertion loss are inversely proportional. That is, the higher the bandwidth, the lower the insertion loss. What I will say, though, for those last three statements, sort of a caveat to that, is they are all very much directly linked to pure sine waves and sine waves only. And we'll explain that as we work our way through this. So if we look and continue with this sine wave idea for a little moment here, if you route your signal through multiple switches, which was the case with the matrix that I was talking about earlier, each time you go through another relay, you pass through what could be looking at something similar to, let's say, a low-pass filter. If you consider each relay as a low-pass filter and you start to stack them up, you start to get multi-order filters, and the graph to the right explains that. So your first relay, the gray line, shows you the 3 dB point and how the signal drops off. If you go through multiple relays, you start to reduce that 3 dB point, and your drop-off starts to increase. It'll never become a absolute brick wall type drop-off, but it increases. And so minimizing the number of bandwidth limiting items in your signal path becomes important. And the same applies to connectors and cabling as well. It all adds together. So when selecting a switch card for your ATS system, it becomes important to understand what the bandwidth rating means for your signal. So most switches are rated by insertion loss at a specific frequency, but it's not always clear how we apply that. Insertion loss generally is a measurement of the reduction of signal power that occurs when a device or a component, switch in this case, is inserted into your signal path. It's often expressed in decibels and quantifies the amount of attenuation that you're going to get when you put that device into your signal path. When a relay with a rated specific bandwidth, or when a relay is rated with a specific bandwidth, it means that it's optimized to work efficiently within that frequency range. For what we're generally talking about here, that's baseband bandwidth, meaning DC to a set frequency, let's say DC to 50 megahertz. When we move our way up to RF, you'll sometimes see this listed the other way as a passband bandwidth. And that may say, like I've got here, it won't start at DC, perhaps 100 megahertz to 3 gig. And it just looks like the image that we've got, but mirrored so that it works in both directions. So once again, looking at a pure sine wave, if the input signal, let's say, is a 60 megahertz sine wave with a 1 volt peak to peak, and we're putting that through a switch or a signal route that's got an insertion loss of minus 3 dB to 60 megahertz, our signal is going to go through, but the output signal we will see, because of this minus 3 dB at 60 megahertz, is going to still be the same 60 megahertz sine wave, but we're going to see something closer to 0.7 volt peak to peak. and therefore our insertion loss is directly applicable there. And I've put a little we've got a repeat of the graph here, but to the right of it, I've shown a sine wave showing, kind of trying to show what I'm explaining here. So we've got our 1 volt peak to peak sine wave here with no loss. But as we increase to 60 megahertz and beyond, therefore the amplitude of our sine wave starts to reduce. And I'll also add to this that whatever you put in your signal path, cables, connectors, switching, your bandwidth is going to be limited to whatever the lowest bandwidth device is that you put in that path. So if it's not the cable or the connector, maybe it's the switch card, or whichever way around it works. Bandwidth is limited to the lowest bandwidth device in your signal path. Now we look at something else a little more different when it comes to this, because our ATS generally isn't working purely with sine waves. We have other types of waveform that we're trying to put through here. One of the very common ones is a square wave. And square waves are really quite complex when it comes to bandwidth and how we apply that. For what we're trying to do here, and looking at a square wave, it could be said that a square wave is made of multiple sine waves at a range of frequencies. And so the lower the bandwidth of your switch, the more it's going to reduce the rise time of your square wave. And it really starts to damage that signal. And an easy way to look at a square wave, generally, and an easy way to look at that square wave is to look at it in the time domain or the frequency domain. In the frequency domain, your square wave has an infinite number of odd harmonics, okay, and each one is slightly lower than the predecessor. So an ideal square wave has a 0 rise time, therefore its bandwidth would be infinite. In the real world, that doesn't exist, and for whatever is generating your square wave, it will give you a specification that states its rise time. Knowing this rise time helps us calculate the minimum bandwidth that we can use to reduce our signal distortion. We tend to use a classic relationship formula here, which is the rise time and the frequency at 3 dBs or minus 3 dBs. And we do that with a figure which we tend to use, 0.35 divided by the rise time. That 0.35 is taken as a inverse of the 10% to 90% of the waveform divided by 2 pi. But if you can apply that to your signal, knowing your rise time and applying that, dividing it by 0.35, you should get a good idea of where your minus 3 dB points will be for your square wave. And from that, you can then select your switching, your cabling, your connectors for your test. Then the next part I'll also cover, it's more to do with, let's say, understanding specifications so much as the best route or way to route your signals through your ATS. And previously I mentioned that you get a large amount of benchtop test equipment rack mounted for ATSs. But a lot of benchtop test equipment, such as oscilloscopes and basic function generators, are what we would term as single-ended. And that means that one side of the output signal is connected to a common ground, and the other side is your actual signal. For most of these devices, the output is a BNC or the input is a BNC, and we use a coax cable. The ground connects to the outer screen of the coax cable, the signal runs up the center. The general idea of this is that the screen shields the inner signal from external noise. And it's the low-cost way to do this because you only need one ADC or DAC per channel, and you can encode or decode your analog signal. The problem comes that any noise that can get through that screen ends up on your signal, and you can't remove it, and therefore that becomes part of your signal. It also, because of this common ground, is susceptible to ground loop effects. Now, there is another way to do this, and as far as signal quality goes, it generally gives us a better result, and that's to go with a differential signal. It's a little more expensive because it requires either an op amp or 2 ADCs per channel. But what it does is, instead of having your signal and a ground, we now have a low and a high signal, and each one are opposite to each other. We then use an ADC or a DSP to reassemble our signal at one end or the other. The idea being any noise picked up on that twisted pair is common to both. So when they're generated, they're inverse to each other. If there's a common to both, say a positive spike or something like that, then we can remove that. And we use a method known as common mode rejection. It's something that's standard op amps, but we can also do it in a digital domain with a DSP. It generally results in a cleaner signal. And I've got an example on the right here. The top is our single-ended, where the white line is your standard ground, and your ADC or your DAC, if it's generating a signal, is just going to go positive and negative with respect to that ground. With your differential, you have 2 DACs, so one is going positive, the other one is going negative. And the math function of the two, the green line, is the actual signal that you're trying to generate. So not all devices or LRUs have single-ended. Quite a few of them are differential input, and therefore it's much better to use this 2-wire transmission line approach and a differential signal. Noise immunity happens, and I've got the example here on the right. Noise immunity happens because, as I said, any noise picked up on the twisted pair is going to be common to both. So if you get a positive spike from whatever happened to turn on or off and created this, you'll see it on both of your high and your low signal wires, and therefore we can delete that or remove that from each, and therefore what we send is what we see at the receiver, regardless of noise that we picked up along the way. There are ways to do this with single-ended devices. If you have a single-ended oscilloscope, you can either get a differential probe for it, or you can use 2 channels in much the same way as we use 2 ADCs or an op amp. We can do the same with an oscilloscope, single-ended, where we use 2 channels. Each channel measures each channel takes it to measure a high and a low input. And then we can use a math function within the oscilloscope to subtract one from the other to give us our resulting differential signal. DMMs are the only exception to the above, where DMMs are differential by default. They have both a high and a low input and generally don't have a reference to ground when they're making a measurement. For signal switching, and I'm talking our basic switch, our multiplexer, or our matrix, you'll find switch cards listed in 2 variants. You'll either see a 1-wire switch or a 2-wire switch. If you're looking at a 2-wire switch, that means that you can now switch differential signals. That is, each relay has 2 connections through into your system. Therefore, when you close a relay to take a measurement or to inject a signal, you're closing both the high and the low of that signal, and therefore selecting the right switch to work with differential or single-ended is important. And if we look right down to the PCB design level and switching, from the outside, a switch card simply looks like a bunch of relays thrown on a card with a front connector and some sort of interface at the back. And if that was the case, then it really wouldn't be conducive to good signal quality. It's like anything. A badly designed PCB is going to lead to reduced bandwidth from capacitive or inductive effects, and for the same reason, it'll also lead to crosstalk or unwanted inducted noise into your signal. maintaining signal quality through the PCB is just as important as maintaining it through your ATE and how you route cables and everything else. It's just done on a smaller level. And we'll see that repeated time and time again the further we drill into this. So if we take a look right back at the initial design stage of a PCB, there are specialist software tools available that enable you to analyze the signal characteristics for whatever type of signal you're intending the device to work with. And then we can run simulation for impedance matching, signal reflections, crosstalk, transmission line effects, and anything else like this. If we can simulate that behavior while we're designing, then we can design a card that is going to maintain your signal quality right the way through. This is no different to the designers of an oscilloscope or a high-speed digitizer, a function generator, or anything else like that. It's the same design philosophy, because at the end of the day, the switch card, your cabling, your connectors are all an extension of your test equipment. And so it's important to ensure good trace routing for your PCB. It's important to ensure good external cable routing for your ATS, and it's also important to select the correct connectors within that cabling to maintain your best signal quality. And there are a few methods that we employ by default with routing cables to and from an ATS by, let's say, separating analog lines from digital lines and ground planes, separating power lines away from both of those as well, and just generally keeping cables in such an order and separated so that you don't collect noise along the way. That philosophy applies right down at the PCB level. It's just as important there as it is with your cabling. So using a switch card that applies these philosophies is important. And so we look at a few things, grounding and layers. So if you look at a switch card PCB, you'll see the top layer tracks and you'll see the bottom layer tracks. But there's a lot more going on between those. You get internal layering as well, and expect upwards of 10 layers on a switch card PCB. And there's a reason for this. It's to do with signal separation. So proper arrangement of signal and ground layers. If you can keep the layers separated, and signal layers should be shielded or distanced from noisy high frequency layers or anything along those lines, power layers and things like that. And we can do that by internal track stack up, as it were. So internally we'll put ground plane layers, and in between that we'll put sensitive signal layers, and it all helps to reduce crosstalk and improve your signal quality. It's also important not to try and swap between layers as well. So trying to keep all of your same type of signals on the same type of layer is important to this setup. And again, it's exactly the same as routing your cables to and from your ATS. And having a signal layer between two ground layers works much like using your screen twisted pair, as discussed earlier, for your differential measurement. And then right the way through, we are looking at what is basically transmission line principles. And it doesn't mean just your cabling, it also means your switch card. It means the connection to your digitizer. It means the connections and connector to your LRU as well. What we're trying to do all the way through and keep in mind too is avoiding any unwanted reflections, noise, distortion, or attenuation. And we do that on a PCB by applying a few things, and as much as separation between tracks as well, other things become important on a PCB, such as track width, dielectric materials, layer stack-ups. Avoiding sharp 90-degree bends on a PCB, interestingly, also helps reduce quite a few issues. And then, much like when you're putting your ATS together, you put your noisy or noise-generating devices at the bottom, out the way in the rack, and your data acquisition further up, where it's less, or in a less noisy location. the same thing applies when you're designing a switch card PCB as well. And as we've already discussed, switch cards generally tend to use mechanical relays. Mechanical relays generate signal noise if they're not correctly placed. And manufacturer data sheets for such things as those relays will show you and specify best practice for placing multiple relays together with minimal effects between them. And this has to be applied. And it's the same philosophy, once again, as everything external on the ATS. And not forgetting that a high-density matrix switch card or multiplexer switch card from that case, you can see upwards of over 100 relays located together on that PCB. So ensuring that you get correct orientation and correct spacing is really important to making sure that you get the best possible signal through, minimizing crosstalk or any other effects from switching multiple relays. Beyond that, there are other ways that we can help improve our actual signal quality. First off, sensor cabling. Signals from sensors and things like this tend to be low, so we're talking low voltages, and analog cables and sensor cabling works as a great antenna for noise and anything else going on. We can reduce that with screening, but we can also reduce that by reducing the actual cable length. So the minimum length that you can run cables within your ATS to your actual LRU really helps reduce that antenna length, as it were, and the amount of noise that you're going to pick up along the way. And therefore, it also becomes obvious that we do the same thing at a PCB level as well. So while you've put all the effort into making sure you've got the right cabling, connectors, and data acquisition or generation hardware within your ATS, it's just as important that the manufacturer of the switch card has done the same thing and made sure that they've got minimum track length, they've applied best practices for shielding and screening, component placement, and selected the optimum components and connectors to maintain your signal quality. And the final part that I want to jump onto while we're at this is standards for ATE or ATS as well. And I want to look at a few things because it helps you, one, maintain your signal quality because you are building a system that's built to set standards, but it also helps you as a time reducer if you're using industry standards to assemble your ATS. And there are a few that I'd like to look at here. One is LXI, which enables you to, or it is a communication standard that enables you to use the same programming API for multiple manufacturer devices and test equipment. It means that you can build your test system and know that the software is able to use the same sort of programming API to control all of those instruments. Plus, they all are detected in the same way and they all communicate in the same way. And it helps you build a system. There are also timing standards because LXI is an Ethernet-based system. Ethernet by default is not time deterministic, but there are methods to make it so. One of those is IEEE 1588, which enables you to use a GPS clock to synchronize all of your data acquisition over the Ethernet with the LXI communication standards. And the other one to look at is OPC. So we said that software is generally bespoke for a test system. That means you normally have to have someone to write your application for that. But it's not always the case. If you can select software from a manufacturer that supports OPC, OPC is a method for softwares from different vendors to communicate with each other. And so you can start to use the software from one manufacturer's product with the software from another manufacturer's product and link them together to get you the data and the automation that you're looking for. So always look for the possibility of using OPC as well. But these are all very much time savers when it comes to building your test system. So that pretty much covers it for me. I've got I've covered pretty much everything to do with why signal quality is important. We've looked at a few of the options that we can do to. We've looked at a few of the options that we can apply to enable good signal quality or to promote good signal quality. And we've also looked at what some of the effects are, such as bandwidth reduction or anything along those lines as well. So I guess that falls over to, does anybody have any questions?
Yes, thanks a lot. Very interesting presentation there. I would just like to remind the audience, if possible, if they have any questions now. I can't see any right now, but if anyone's got any, now is the time to submit them. I've got a couple of questions myself. I mean, first of all, I thought it was very interesting the way that signal quality can be affected, right down to the levels of the PCB design. I thought that was fascinating. But are there any? What are the kind of common pitfalls that are normally made, or that you see at that level, or any level to do with signal quality and automated test systems?
The biggest issue generally comes from placement. And the routing of cabling or PCB layers and tracks, the careful routing of them to make sure that these are not located near anything that is noise inducing. The biggest pitfall is putting your sensitive analog line right next to your noisy power supply line or something along those lines, or something that's switching a high power. The general issues tend to come from EMI or electromagnetic interference.
Okay, thanks, Nathan. And I mean, is that what you commonly? That's the sort of common advice you give to people. That's the sort of main message of this, is it? When designing that they're the main sources, and that's what you should kind of keep away from.
Yeah, it is very much a case of paying attention all the way through to your signal routing. You've paid a lot of money, or you invested a lot of money into your data acquisition and your signal generation. Don't throw that away by bad signal routing and bad selection of components.
Okay, sure. I've got a question here from Jeff Stevens. I'll just say it first and then publish it so everyone can see it. But he's asking, do we have a tool to determine additive insertion loss in switching systems?
There are a few that are available on the internet that you can use for this. In fact, there's a few good ones. I can't think from the top of my head what the addresses are for them, but a quick search will find you a few that really do work very well for doing that.
So, I mean, I'll just put that out there again. If there's any more questions, we did only have a few minutes. We do only have a few minutes. If anyone's got any more, that would be great, but maybe not. So, if you're happy, Nathan, I'm happy to end things there. If there's anything you'd like to add, perhaps.
No, just thank everybody for listening, and there's a lot of information out there on the internet on how to achieve this, and just keep a close eye on what you're doing with your cabling and your switching.
Good stuff. Okay. All right. Well, thank you again, Nathan. This presentation, I can see a question here about whether or not we can the presentation is share. You can download it and share it. The whole webinar will be available to watch again afterwards. You'll receive an email containing the link for the webinar, and I'm sure Nathan will be able to get in touch. He'll have a record of all the questions.
Yes.
So he'll be a presentation to you. Okay, so thanks again, Nathan. Thank you, everyone in the audience, for your attention, whether you're watching live or in the future at some date. And yeah, have a great day.
Okay, thank you.
Thank you. Bye-bye.